You probably think the internet is up there, on thousands of orbital satellites, high above your head, drifting in the silence of space. You imagine data beaming down from Starlink or GPS constellations, connecting every corner of the planet through the air. You're wrong. 99% of the digital world isn't in space. It's here, at the bottom of the ocean, in the dark, crushing pressure of the abyss. Right now, as you watch this, your connection to the global web is likely traveling through a tube of glass and copper, resting on the seafloor, miles beneath the waves. In this video, you'll learn how 10,000 volts of electricity hidden under the weight of the deep keep our modern civilization alive. Look at a map of the world's undersea cables, and you'll see a planetary nervous system. Over 400 active cables stretch across more than 800,000 miles, enough to wrap around the Earth 30 times, or to reach the moon and back, and then some. These aren't new inventions. The history of this engineering feat goes back to 1858, when the first telegraph cable was laid across the Atlantic. It was a brutal, difficult task that barely worked for a few weeks, but it proved one thing: humanity could bridge the oceans with wire. Today, that thin copper wire has evolved into a high-tech, armor-plated lifeline that carries the entire economy of the 21st century. The core of this engineering marvel is a set of glass fibers, each no thicker than a human hair. This is fiber optics. It carries data as pulses of light at nearly 2/3 the speed of light in a vacuum. Every email and bank transfer is translated into billions of microscopic flashes per second. But light has a problem. Even the clearest glass isn't perfectly transparent. As those pulses of light travel through miles of fiber, they begin to scatter and fade. The signal becomes weak and distorted. To prevent the signal from dying, engineers install repeaters. These are massive titanium cylinders, underwater amplifiers. Every 50 to 60 miles, the cable enters one of these 300-pound beasts. Inside, lasers detect the faint incoming signal and re-energize it, launching a fresh, powerful pulse of light for the next leg of the journey. But repeaters need power, constant, unwavering electricity, to operate for 25 years without human contact. This is where engineering gets dangerous. To overcome the electrical resistance of thousands of miles of cable, shore stations must pump a staggering 10,000 volts of direct current. This isn't the kind of power in your home. It is a massive pressure of electrons pushing halfway across the planet. Imagine the challenge. You're pumping 10,000 volts at depths where pressure is 600 times that of the surface. One microscopic leak, and the seawater will short the system instantly. The cable is an engineering sandwich: fiber at the core, copper conductor, steel armor against pressure, anchors, and even shark bites. A thick, waterproof polyethylene skin wraps the entire assembly. Near the shore, the cable is as thick as a human thigh. In the deep ocean, it is as thin as a garden hose. But here's the part that defies logic. Most circuits need two wires, a positive and a negative. Laying a second return cable would cost billions. So engineers use a planetary scale trick. They use the ocean itself as the second wire. The current travels down the copper core, powering every repeater along the way. When it reaches the far side, it is released into the sea through massive grounding electrodes buried in the seafloor. The salt water, dense with minerals and ions, is a perfect conductor. Because the ocean is so vast, its electrical resistance is nearly zero. The current flows through thousands of miles of deep sea water back to the starting station, allowing the circuit to close. Every time you load a web page, you are technically using the entire Atlantic or Pacific Ocean as a part of your computer's hardware. Why do we still mess with this heavy hardware in the age of Starlink? Physics. Satellite signals must travel to orbit and back, a journey of 44,000 miles. Even at the speed of light, this creates a physical delay, or latency. While a few hundred milliseconds might not matter for a casual video call, it is unacceptable for the real-time systems that run our world. global banking, high-frequency stock trading, and the massive cloud computing grids that power AI, they all require the speed of light through glass. A single fiber optic cable carries more data than an entire fleet of satellites combined. It is the difference between a garden hose and a massive river. Space is the future of coverage for remote areas, but the underwater copper and glass skeleton is and will remain the backbone of the global economy. Without 10,000 volts pulsing through the abyss, our digital civilization would freeze in an instant. No global trade, no instant communication, no cloud storage. The next time you load a web page, remember the silent power working miles beneath the waves. It is a hidden world of glass, copper, and titanium, a testament to human ingenuity that keeps 7 billion people connected every single second. What surprised you the most? The 10,000 volts, or the fact that the ocean is part of the circuit? Let us know in the comments below. If you enjoyed this deep dive, don't forget to like and subscribe to What, Where, and Why. Thanks for watching.